Thanin from Burapha University in Thailand. Today I will present about the comparative analysis of time series forecasting method for dengue fever in Thailand, especially in ECC zone. This is the agenda of today's presentation if you follow these topics. First of all, I would like to give some background about the dengue fever. I think everybody knows well that the dengue fever is the serious harming to our life. It's kind of the mosquito-borne diseases, which from 2023 there were more than 390 million infections happened in 2023, and from that amount, around 96 million showing the clinical symptoms. In Thailand, as we know that the dengue fever is endemic in Thailand, but there is very interesting case that the abnormal heavily outbreak usually happens in Thailand every 2 or 5 years. For the rapid urbanization and population mobility and climate change could increase the risk of the transmission. So in this case, especially for the developing region like the EEC zone, I will give the more information about EEC zone in the next slide. So let's know about the regions in Thailand. In Thailand, we separated regions into 6 regions, include the central, northern, southern, western, eastern, and the northeastern. In the eastern region, we have 7 provinces, including Chonburi, Chachoengsao, Rayong, Prachinburi, Sakeo, and Chantaburi, and Trat. And partially from the eastern region, we have 3 provinces included into the EEC zone. Actually, the EEC stands for the Eastern Economic Corridor. In this EEC zone, it's kind of the big mega project from Thailand government to support the investor, to attract the investors from abroad to come and invest the industrial in Thailand with many advantages. For example, about the tax and the facility. For example, like the high-speed railway, the airport, and the seaports. So we can expect that the economic in this area will grow a lot, and also many people will move in. For the research objective, we would like to compare the performance of 2 forecasting methods, which are ARIMA and LSTM, with our dataset. And then we evaluate them with 4 matrices, which are MAE, MSE, IMSE, and MAPE, to identify which model could be the most suitable for the different data patterns, and also to provide a decision framework for the local and regional health management. This is our framework, starting with the data acquisition, and then we do the data pre-processing before the analysis and exploration. After that, we try our experiment with the different way of the train and test set splitting. For the first one is the ratio is 70 and 30, and the second one is 80-20, and last one is 90 and 10. So we split our dataset into the training set and test set following this ratio, and then we do the model selection for forecasting and generate our prediction result. After that, we compare the performance after the model validation with using ARIMA and LSTM. I would like to mention more about our data acquisition. For this dataset, we acquired from ida.informatics.buu.ac.th, which is a data sharing platform that we work together with the Korea Institute of Science and Technology Information in Korea, together with our university, Burapha University, for under our MOU and the collaboration research activity. For the data exploration, we try to explore the dengue trend from every provinces in Thailand, but we grouped it into different regions for easier to see the pattern, because we have totally 77 provinces, which quite difficult to see the detail when we combine them together. Then we split it into by each region. We can see that most of the region are not really follow the same trend, but few of them may share some highly correlation together. For example, like for the central region together with eastern region and western region is quite similar, that around 0.7 something. And the highest one was eastern region with the western region. For the model and evaluation metrics, we use the ARIMA and LSTM for the evaluation metric. I use MAE, MSE, RMSE, and MAPE. After our experiment, we saw that using the combination of 80 and 20 give the best result. We can see that it's outperform if we compare with RMSE, MAE, and MSE. But in case of MAPE, actually it's slightly increased a little bit if we compare to another combination. For the regional result, some regions which include eastern, western, northeastern, and central region, which the trend of the disease is quite seasonal and has a similar pattern. So ARIMA can predict very well. But in some region, like in northern and southern region, which is kind of non-linear and quite fluctuating pattern, the LSTM can perform better. And if we see it in the province level, smaller level than the region level, it still show in the same way that for in the province that has quite clear pattern and seasonal pattern, ARIMA can perform well, while LSTM could perform well in kind of non-linear or kind of the messy seasonal. From the discussion of our model, we think only one size fits all is not exist. To use the only one single model is not universally superior. And ARIMA could perform well with the linear pattern when LSTM could perform it in other way. This comparative framework helps the researcher and policymakers choose the right forecasting model for their region. And for the conclusion and future work, this study could provide a comparative framework for dengue forecasting in Thailand, especially in the EEC region. And for the future work, we try to hybrid together the model of ARIMA and LSTM together. After that, we also would like to integrate the climate factor and socio-economic variable as the input feature. And lastly, for the real-time forecasting dashboard, or apply kind of the explainable AI instead of the current model that we are using. Lastly, about the acknowledgement, we would like to thank you to Burapha University for Faculty of Informatics and Faculty of Science and Social Science, and also our partner Korean Institute of Science and Technology Information. Thank you very much.